Hey folks, today we're going to build on the ideas we've been discussing recently regarding the convergence of power series, and I want to take you back to the geometric series we talked about way earlier in the course. And remember that it has this general form and it converges when the value of r is less than 1 in absolute value. And remember, in that case, it converges to c over 1 minus r, provided that the absolute value of r is less than 1. In other words, in other cases, it diverges. Well, we can build a function out of this, right? Because we can represent a function. Let me write down what would happen if I replace that r with x's. Imagine I just had the series, let's ignore the c for now. Imagine I just have the series x to the n. This is a power series with center at 0. And it just looks like 1 plus x squared plus x cubed, I missed one, and then x to the 4, and so on. Forever, right? And that's going to converge when? Well, converges when r, in this case x, is less than 1. So we have a power series, and we know exactly when it converges, and we also know, because we showed this, it diverges when x is not less than 1 in absolute value. In other words, x is greater than or equal to 1. So this is a power series that we've been talking about, and it has a radius of convergence of 1. And it has a center at the origin, at 0. So it has a radius convergence of 1, because x minus 0, absolute value, is less than 1. And we know what it converges to. In this case, c is 1 and r was x, so it converges to 1 over 1 minus x. So we've actually found a way to represent this function as a power series, right? This power series and this function will provide the same value, will be the same value, as long as the absolute value of x is less than 1. In other words, those two things are equal when x is bigger than minus 1 and less than 1, when the absolute value of x is less than 1. This is defined whenever x is not 1, right? This is defined at minus 5, and it's defined at 12, and it's defined at 100. This is not. So the idea here is we have a power series representation of the function, but only on some of the domain of the function. So these two things are equal, but only when x is between minus 1 and 1. When x is greater than 1 or equal to 1, or it's less than or equal to minus 1, then this function does not produce the value that that series would produce, because that series does not converge. It does not produce a finite value. Whereas I can plug minus 5 into this formula and get a number. But they're not connected outside of that range. And that's the key idea to representing functions as power series. So what we've shown with this argument is that 1 over 1 minus x is equal to this power series for all x less than 1 in absolute value. You'll find this nice formula in the book. Let's look at another example. Here's a function that's quite similar to what we just discussed. So comparing this function with that function, I could imagine writing, or essentially replacing the x here with negative x squared. So in other words, imagine I took the sum from n equals 0 to infinity of not x, but negative x squared. And if I do that, as I start to write that out, I've just literally replaced the x to the n here with, I've replaced the x here and the x here, I've replaced them both with negative x squared. So that will lead me with 1 minus, the next term is x squared, plus x to the 4, minus x to the 6, plus x to the 8. You can keep going and doing that forever, and that's going to converge. Well, if it converges, it is a geometric series, right? It's a geometric series. It converges when the absolute value of that minus x squared, the thing I replaced the x with, because I'm replacing the x with minus x squared everywhere, there, and there. And so it converges. That's the same as saying x squared is less than 1, and that is the same as saying just the absolute value of x is less than 1. So this also converges in that same region, and what we're going to get it converging to is 1 over 1 minus x squared, because that's what I replaced, right? And that's almost the function we want. Now notice that the function I actually want is 2 over 1 plus x squared. So I'm going to go through and double everything. Double that will give me 2, doubling that will give me 2, doubling that then simplifies to what I wanted in the end, which is 2 over 1 plus x squared. So what we've shown here is that 2 over 1 plus x squared is equal to that power series up there, 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8. Another way of writing it would be minus 1 to the n, and then there's going to be 2 times x to the 2n. Or I could leave it written like that. Either way, it's the same series. And that is going to be convergent. The series is going to be convergent, which means these two are equal when x is less than 1. Right? The idea here is this series is going to converge to that function, provided the absolute value of x is less than 1. Now, the number of series that we can actually build from the geometric series itself is pretty limited, right? I could make a bunch of functions that look very similar to 1 over 1 minus x, and I could plug in different values for x, and I could get them to converge on, find the region where they converge. Let's do one more. In this case, it's looking similar, except there's a factor of 3 there that I don't have in this general form here. But I could always factor that 3 out of the denominator, right? This is 3, 1 minus x over 3. And so this is going to be 1/3, if you like. I could put that on top. 1/3 of 1 minus x over 3. And so with that factor of 1/3 out the front, we can rewrite this expression like this. And then we can use the power series. So we know that 1 over 1 minus x is going to be the sum of the x's to the n. So in this case, we're going to get the sum of the x's over 3 to the n. We're going to sum from 0 to infinity of x over 3 to the n, because here I've literally replaced what was an x with an x over 3, so I do the same thing here. And then you can simplify that down to, well, that's the sum from 0 to infinity of x to the n, and if I factor that 3 in as well, then I've got 3 to the power of n plus 1, which we could then write out, right? The first term is 1/3, and then the second term is x over 3 squared, x squared over 3 cubed. You get the idea, x cubed over 3 to the 4, and this continues forever. And that's going to converge, right? This is going to be equal. These two things are going to be the same. The power series representation of this function is going to be this, provided that the quantity, which in this case was x over 3, is less than 1, right? Or in other words, x is less than 3 in absolute magnitudes. Or in other words, x is between minus 3 and 3, because that's the same inequality. And so what we've done is we've shown that this series is a power series representation for this function when x is between minus 3 and 3. This function is defined for all real numbers except for 3. So this function has values everywhere except 3, but it's only got this power series representation when x is between minus 3 and 3, because otherwise this series does not converge. It might go to infinity, it might go to negative infinity, it might oscillate, but it doesn't converge to a fixed number. And so this is the power series representation only in that limited sort of domain. So we've seen a few examples here where we've taken this geometric model and we've used it. That's a pretty special situation where you can directly relate it to the to that geometric kind of sum formula. Let's stretch this a little and talk about Theorem 2, which talks about the ability to differentiate and integrate term by term. And what it's telling us is if a power series is differentiable within a certain radius of convergence, right? Again, this is a radius of convergence R centered on the center C, then you can integrate and differentiate term-wise. In other words, you can differentiate every term. So if this is the nth term, the derivative of the nth term is going to bring the n down. Look, brings the n down and reduces the power by 1. And that's going to do it on every term, and that's going to give us the derivative of the power series. But that derivative of the power series, the thing on the right here, is going to be equal to the function on the left, the derivative of the function. And similarly, you can integrate term by term. So let me give you an example. We've just shown that we can represent the function 1 over 3 minus x using this power series. So what this theorem's saying is I can use the derivative of this, and we know the derivative of 1 over 3 minus x. It's going to be 1 over 3 minus x all squared, just differentiating it. Well, this theorem tells us that if I just differentiate that function, I can also just differentiate the power series term by term, and that gives me a power series for this derivative. So the derivative of this power series is going to be 1 over 3 squared plus 2x over 3 cubed, plus I'm just differentiating here term by term, term-wise in other words. The next one's going to be 4x cubed over 3 to the 5, and the next one's going to be 5x to the 4 over 3 to the 5, 3 to the 6, and so on. And so what this theorem does is let us build new power series for functions that we didn't already have because we know how to differentiate, right? So I differentiated the power series, I differentiated the function, and that produced a power series that I didn't previously know. Instead of writing out each term in the series and then differentiating those, as I've just done, we can actually do it on the actual power series itself. So let me show you what I mean. Taking that series that we were just looking at, I can take its derivative, and again the derivative is 1 over 3 minus x squared. That gives us the derivative of the function. It will be equal to the term-wise derivative of the terms. Right? So I'm just differentiating the power series term-wise, so doing it one term at a time. And starting to plug in, you can see what this will give us. Notice what all I did. I brought the x down because I'm differentiating a power of x. So the x comes down and I reduced it by 1. So here is the appropriate series. If I plug in n equals 0 now, I get 0 times x to the, what's that, minus 1. Well, that term disappears anyway. So we'll get a 0. And then when x is 1, I'm going to get x to the 0, which is 1. X is 1 over 3 squared. And the next term is going to be now n is 2. So it's 2x to the 1 over 3 cubed. And the next term is n is 3. So it's 3x squared over 3 to the power of 4 now. And then n is 4, so we're going to get 4x cubed divided by 3 to the power of 5, and so on. And here's what we found last time, right? They're the same. It doesn't matter which order we do it, which way we do it, whether I actually write out the power series and differentiate term by term, or whether I just formally differentiate this general case, right? All I did was take that and differentiate it directly. If I wanted the terms, I could then write them out. But that gives me a power series, and again this power series is going to converge because our theorem says it converges in the same interval, right? Essentially if the original power series has a radius of r, then the derivative will also have a radius of convergence of r. So we know for this series to begin with, it worked when x minus 0, the center was 0, was less than 3, and so we know this will work when the absolute value of x is less than 3. In other words, it's got the same center, the same radius of convergence, so that power series representation for 1 over 3 minus x squared will give us a convergent series that represents that function when x is between minus 3 and 3. So the fact we can integrate and differentiate, going back to the theorem, we can integrate or differentiate term by term, then gives us a new way of building functions that we didn't previously have. Let's do another example. So in this case, we want to find a power series representation of the natural log of 1 plus x. And thinking about that, I don't know how to do it, but I do know one connection, and that's the integral of 1 over 1 plus x. The integral of 1 over 1 plus x is the natural log of the absolute value of x plus 1. Plus a constant. And so that gives me some hope because this I know the geometric series for. Right? If I can find the geometric series representation for this, then I'll be able to integrate term by term and get the geometric series for log. Going back to what we know 1 over 1 minus x is this summation, so we conclude that 1 minus x is going to give us what we want. That's 1 over 1 plus x. And that's going to be the sum from 0 to infinity, this infinite geometric series, of minus x, because I've replaced x everywhere, with minus x, so it's going to give us minus x to the power of n. So in other words, 1 over 1 plus x is going to be, the first term is going to be 1, everything to the 0 is 1, and then we'll subtract x, and then we'll add x squared, so it's the alternating version of this series over here. So when you're subtracting in the adding in the denominator, you get that alternating series, which is equal to the function when the absolute value of x is less than 1. Okay, so then we know that the natural log of x plus 1 is going to equal, well, that integral plus a constant. So it's going to be the integral of 1 over 1 plus x. I'm just going to throw the constant on this side. So I'm going to put it there, minus a constant, because it was over here before. So if I just rewrite that, I'll put it on the other side. And that's going to be the integral of that series, 1 minus x plus x squared minus x cubed plus x to the 4. You get the idea. And we just have to integrate those terms, and then we're going to have the constant. Right? As I integrate, the first one's going to be x, the next one's going to be a half of x, and then we're going to get, what, a third of x cubed, and the next one is a quarter of x to the 4, and then a fifth of x to the 5, and then a sixth of x to the 6. It's still alternating, and you can look at that hopefully, and there's going to be a plus c, so I'm going to write that at the front. I'm calling it minus c, but I'm putting it at the front there, just so it doesn't conflict with my dot, dot, dot. And I know that is going to be, well, I could write the general form of this because it's fairly straightforward. When I look at it, the first one's x, and I could think about this as 1 over 1. So this is x to the n divided by n. X to the n divided by n, and it's alternating, so I'm going to put an n minus 1 there. So going from 1 to infinity, we'll end up with something like that. I think that's right? Because we'll get x to the 1 divided by 1 minus x to the 2 divided by 2, x to the 3 divided by 3, and so on. I could have done it by just directly integrating this term here. Let me think about what we mean by that. I could have literally plugged in my power series representation for 1 over 1 plus x into the integral, and then just integrated every term. What this theorem is essentially telling us is I can swap the sum and the integral. So instead of integrating that entire sum at once, I can integrate each term. So I'm going to get this minus 1 to the power of n, x to the n dx. I'm going to integrate that, and then when I'm done, I'm going to add up the result. That's essentially what's happening here. And when I do that, I'm going to divide, the minus 1 to the n doesn't change, it's just a constant. X to the n, that's going to give me 1 over n plus 1, x to the n plus 1, and n is going from 0 now to infinity. But if you start writing that out, and I'm going to write the c at the front just to avoid confusion. If you start writing that out, what that looks like, you'll see that it's exactly the same as we had before. When n is equal to 0, we get x. When n is equal to 1, we get a half of x squared, and it's alternating. And so it's just numbered in a slightly different way than my guess before, but it's the same power series, and that's the important thing. And our theorem tells us that this is going to work. This is going to be a valid power series representation for x less than 1 in absolute magnitude, because that's where the original power series for 1 over 1 plus x was valid. And that means once I've integrated, the power series is still valid there. So I've got this expression for the natural log of x plus 1, but of course natural log doesn't involve a constant. So how do I make sense of that constant? Well, let's think about that for a sec. If I plug x equals 0 in here, all of this will disappear. Oh, I forgot to write the c on this side, didn't I? So this is minus c plus all of that stuff, right? There's all of that stuff, and then the minus c was still there. If I plug x equals 0 in here, all of this goes to 0. All of that goes to 0. So literally, when x is equal to 0, I can plug in natural log of 0 plus 1 is equal to minus c plus that sum. And if I write it the formal way, n is 0 to infinity of minus 1 to the power of n, 0 to the power of n plus 1, because I plugged in x equals 0, right? And that is 0. I'm just adding 0 up. Lots and lots. And the natural log of 1, that's the natural log of 1, that's equal to 0. And so from this, I conclude that c is equal to 0. I could use any value of x here. Using x equals 1 lets me actually see what the value is going to be. It's a really good one to choose because it makes all these terms disappear, right? It makes all of those terms disappear, and so I don't have to worry about adding an infinite sum and finding out what the value is. And so putting all of that together, that tells us then that we've found that the natural log of x plus 1 is equal to, what was it, x minus a half x squared plus a third x cubed minus a quarter x to the 4. We've got now an infinite series that represents, and it's an alternating series, that represents the natural log of x plus 1. And that's true, because it converges in the same region, it's true provided that the absolute value of x is less than 1. And another way to say that is x is between minus 1 and 1. In other words, x plus 1 is greater than 0 and less than 2. That's the value we're actually taking the log of. And notice I didn't say it carefully at the time, but the natural log of the absolute value, I dropped the absolute value because I knew x plus 1 was bigger than 0. So I'm taking the natural log of a positive number here. And speaking of natural log, we can extend this idea and think about the natural log of x itself by shifting this whole thing 1 unit to the right. In other words, replacing x everywhere with x minus 1. And doing that produces a series which is centered at 1, because I'm replacing x everywhere with x minus 1. And so if I were to write that out, we start getting terms similar to above here, but now it's a power series that's centered at 1. And it's got a radius of convergence of 1, because we know that this thing is a power series representation for log, provided that the absolute value of, well, we've turned it into x1 minus 1, is less than 1, which means we're centered at 1 and has a radius convergence of 1. Another way of writing that is x minus 1 is between minus 1 and 1. And another way of writing that is x is between 0 and 2. So we have a power series representation here, centered at 1, radius 1, for the natural log of x. So what we've done in this section is build a whole lot of functions that have power series, but they're a very specialized collection of functions, because somehow I've related them back to that basic power series, and I've done some for the geometric series, and I've done some integrals and derivatives and things. Our goal is to extend that to more general kinds of functions. And that's what we'll do soon, but in the next section, we'll think about how we approximate functions and what this kind of idea we've got really means. Thanks for tuning in. I'll see you soon.